So chapter 5, performance of the feedback control systems, that we started last week, and we discussed why feedback systems give better performance as compared to your open loop system. We can set the transient response, we can set the steady state response, because the actual output is compared against the desired output, which is the input. And based on that, we can control the parameters of the controller. We discussed that what are some of our input signals that we use to test the system. And specifically, we discussed 4 input signals: unit impulse, step, ramp, and parabolic. Impulse signal is something that is theoretical signal because it has infinite magnitude in analog systems. So we don't really use that signal, but rest of the signals we can use to test response of a feedback control system. And the nature of your input signals can be given by RT is equal to A t to the power n, where n for 0 is going to give you a unit step signal, n is equal to 1 is going to give you a ramp signal, and n is equal to 2 is going to give you a parabolic signal. And of course, the Laplace transform for each of the signal can be given by that expression, n factorial over s to the power n plus 1. We worked on this example, unit step response of the closed loop system, and then we discussed how to plot that, as we did in today's quiz as well, how to plot the response without going into the time domain, just from the frequency domain, how to plot the unit step response of the system using first defining the transfer function in MATLAB and then using the step command. So now we're going to look at specifically second order system and second order underdamped system that are oscillatory in nature. And this is something we also discussed in chapter number 2. We did an example and we used one of the transform pair for the second order system to write down the time domain nature of the second order system with that pair. So in general, roots of the denominator of transfer function, we call them poles, and the roots of the numerator, we call them zeros. So let me see where my pen is. You're going to be seeing these terms over and over again, poles and zeros. So make sure, understand these terms are that whatever is in your denominator, when you factor that out and calculate the roots, those roots are called poles of the system, and whatever you have in the numerator, if you factor that out and calculate roots, those are called zeros of the system. So those terms are going to be repeated throughout the course. Output of the unity feedback system, as shown in example 5.1, can be given by, so example 5.1 that we discussed over here, this example. Output can be, the transfer function can be represented by this expression. We go back. We solve this transfer function specifically using the second order system and the pair that we created using the second order system. If you want to solve the same thing using the Laplace transform pair from chapter number 2, which is given right over here, then first we have to write the equation in terms of omega n square over s square plus 2 zeta omega n s plus omega n square. So let's do that so that we can understand and see if we get the same result as we did in chapter number 2. 2 over s square plus s plus 2. This is our expression. So ys is 2 over s square plus s plus 2, right? That's ys. Rs, of course, is a unit step function. 2 over s square plus s plus 2. If you compare this, and then, of course, Rs, if you compare these two, then you can determine the value of omega n, which is the natural resonant frequency, the frequency with which your oscillations are going to happen, and zeta is the damping coefficient. So if you compare these two, what do you suggest? What is omega n square and what will be the value of zeta? Omega n will be square root of 2, and then zeta will be equal to so 2 zeta omega n is equal to 1. 2 zeta omega n equals 1. So zeta will be equal to 1 over 2 omega n. Right? So 1 over 2 times square root of 2. Whatever the result is going to be, anybody can calculate. They can. Zeta between 0 and 1 is going to result in an underdamped system. If zeta becomes 1 or greater than 1, that's zeta is equal to 1 is the critically damped system, and if it is greater than 1, then it's going to become, no, zeta is equal to 0 is critically damped system, is it? Or 1? I think 1 is critically damped system. And if zeta goes beyond 1, then it's going to be an overdamped system. So for underdamped response, we always want the value of zeta to be between 0 and 1. And that is going to give you an oscillatory response with a peak value, and then it's going to settle down to a steady state value. And definitely this is less than 1. So zeta .3536. Yes. I'm sorry? No, zeta cannot be negative for the system, no. Unless you want the system to be unstable. For unstable system, yes, it can be negative. Because your second term, so again, we're going to discuss this in, I think, chapter number 6 about the stability of the system. But for stability of the system, the sign of all of the terms in the denominator, they have to be same sign. If there is a sign change, then you may have an unstable system. Basically. All right, so with these, if we use these values, and it's pretty straightforward because this is actually written in terms of this omega n square over omega n square. Now, remember in chapter number 2, there was a problem that we did based on this, in which the numerator was not equal to the omega n square. So we wrote down the expression, divide and multiply the expression by omega n square, and then rewrote the numerator as a multiple of the whole expression. And that multiple carried out in your time domain expression. In this case, it is exactly how it is written in the generic expression, with omega n to be square root of 2 and zeta to be 0.3536. So with these values, when you calculate the time domain response for your unit step function, ys is going to become 1 over s times this, and the time domain response is given by this expression. So we know the value of zeta, we know the value of omega n. We can just plug in all the values in here and get our time domain response. And it is plotted in that figure for different values of damping coefficients. As you can see, 1 is the black one, overdamped response, 2 overdamped response, but if it is below 1, then you will always have a peak and then it comes down. So it will always be an underdamped response. The smaller the value of zeta, the higher the peak is going to be and more oscillations are going to be in your response. So before it settles down, you're going to have oscillatory nature of the system if the value of zeta is quite small. The steady state error is always 0 because the output will always reach to 1, but the transient response matters because if your system is moving too much within that transient period, oscillating too much, that's not safe for the system. So really based upon your system requirements, you have to choose the value of zeta, you have to choose the value of omega n and create the system such that the peak value that you're looking for, it is obtained, the time in which it settles down, it is obtained, and all those things. Second order system, oscillator systems are very common, underdamped system in practical world. But again, they have to be designed properly, otherwise oscillatory nature can be really dangerous for the system. So for zeta is equal to greater than 1, the response will be overdamped, as I mentioned. And for equal to 1, it is critically damped response. Some of the parameters for second order underdamped systems. You have, in this figure, it is given to you. I'm just going to mention those things. Swiftness of the response, measure in the rise time, and the peak time. So there are two rise time given over here. One rise time, the bottom one, is from 0 to 100% of the response. So when it goes from 0 to 1, there's one rise time. And then the other rise time is when it goes from 10% to 90%. 0 to 100% is generally used for underdamped system rise time, and 10 to 90% is generally used for overdamped system. Percent overshoot is defined by this expression, MPT, which is basically your peak value, which is right over here, minus the final value, which is the steady state value, over the steady state value. So peak overshoot is an important parameter. And peak overshoot is given in percentage, 36% peak overshoot, 40% peak overshoot. And that basically tells you the ratio between the peak value minus the final value to the final value, as how much it overshot with respect to the final value, how much the system overshot. And that's a parameter that is used to measure the performance of the system. Settling time, the time required for the system to settle within a certain percentage of the input amplitude. So settling time, for example, here, which is given to you right here. So you choose a value of zeta, and you see it is oscillating between that value, going up and down. And the first time it goes to the value 1 plus delta, and then it does not come out of these red lines, that time is considered as the settling time of the system. So you have a threshold 1 plus delta to 1 minus delta. Let's say delta is 0.05. So as long as it is between 1.05 and 0.995, and it's not going beyond that range, the first time it happens, that time is going to be considered as the settling time. And we're going to say the system is settled down enough such that it is no longer oscillating as it was oscillating before that. We discussed settling time in circuit analysis, if you remember that as well. So that's the concept of settling time. In general, 5 time constants in general are good enough to estimate that the system has settled down to its steady state value, 4 to 5 time constants. But to be exact, you can calculate the settling time as well for the given value of delta. Oh, by the way, time constant. So how are you going to find the time constant? Actually, it's there, right there somewhere. So yeah, so settling time in this case, they are calculating as 4 time constant, as you can see. And time constant from this YT, of course, remember time constant goes with the exponential decay response, how fast the curve is going down or whatever the exponential is. So as we discussed several times, we have to look at the time constant from the perspective of e to the power negative t over tau. And that tau is the time constant. So in this case, when you have e to the power negative zeta omega n over t, we can write this thing down as e to the power negative t over 1 over zeta omega n, which is the same way, which is the same thing as e to the power negative zeta omega n times t. So 1 over zeta omega n is considered as the time constant of the system. And the settling time is approximately, as it is given here, 4 times the time constant, or 4 divided by zeta omega n. And that is for the 2% value of delta. 2% of the final value. Steady state error, we know, is the difference between input, which is the step response, and the final value of the output, which is the YSS. That's a steady state error. Transient response of the system may be described in terms of 2 factors: swiftness of the response represented by the rise time and the peak time, as I mentioned before, and the closeness of the response to the desired response as represented by the overshoot and the settling time. For the second order underdamped system, peak time can be calculated by this expression. Again, we're not going into the derivation, but this is used to calculate the peak time. And of course, if you have plotted this curve, then you can always see with your cursor what is the corresponding value of x for the peak to occur, and that's the peak time right here, right, this one, when the peak is going to happen. Mathematically, it can be calculated using this expression. Response at the peak time, which is the peak response, can be calculated using this expression. Again, graphically, you can always go and put your cursor over here to see what is the value of y, and that's the peak value. And mathematically, of course, it can be calculated using this expression. And the peak overshoot, to calculate that, of course, we know the generic formula of peak overshoot is peak value minus the steady state value of the output divided by steady state. But if you drive it in terms of from the equation, the time domain expression, then it's going to come out to be in percentage 100 times e to the power negative zeta pi over 1 minus zeta square. So these expressions can be used to calculate those values and can be compared against the observed values from the plot. Peak overshoot versus damping ratio can be observed from figure 5.3 and plotted using 5-10. This, as damping ratio decreases, peak overshoot increases. As we saw earlier in here, damping ratio decreases, peak overshoot increases. The peak time for a given value of omega n decreases with a larger value of zeta, as can be seen by 5.8, which is this figure. As your zeta value is becoming large, then the peak time for a given value of omega is going to decrease. This is a plot from the book, or I don't know if it's from the book or I got it from online. Could be from the book. Normalized peak time omega n tp and peak overshoot can be plotted against zeta. So zeta is on your x-axis. You have peak overshoot on the left side and omega n tp on the right side. And when we plotted the two equations, peak overshoot and then omega n times tp, so we multiply tp by omega n and plotted pi over 1 minus zeta square as our scaled value of omega n t. Let's see, shown in figure. So as we can see, as the damping ratio is increasing, then your scaled value of omega n tp, that is increasing, and peak overshoot as the percent overshoot, not the peak overshoot, sorry. As the damping ratio is getting smaller, the percent overshoot is increasing. As it is getting larger, of course, the percent overshoot is getting smaller because your system is heading towards overdamped system from underdamped system. So your overshoot becomes smaller and smaller. Okay, let's take a break and then discuss effect of the third pole on the second order system after the break. Okay, so the second order system we just discussed. In this topic, we are seeing as how the second order system is going to be affected if we add one more pole, that is one more factor in the denominator. We make it a third order system. So we do have, as you can see, two factors. One factor that represent the second order system, 1 over s square plus 2 zeta s plus 1. Specifically in that case, omega n is equal to 1. And then we added another pole, gamma s plus 1. Now the idea goes back to what we discussed about the dominant root, that which value of root on the s plane on the real axis is closer to the, which value of the pole is closer to the origin. This is the s plane. And of course, you have the real values, and then you have your imaginary value. S, of course, is sigma plus j omega, or omega n in this case, for second order system. So what you see over here on the slide is, as you can see, the S plane right here. This third order pole, which we can also write as zeta S plus 1 over gamma, sorry, not zeta, 1 over gamma. So the whole idea is, if the root of this, or the pole basically, 1 over gamma, or negative 1 over gamma, is far enough from zeta omega n, which is the time constant of the system. If it is far enough, again, I'm assuming omega n is equal to 1 in this case, so it's basically zeta. So if it is far enough from zeta, then the exponential function associated with this is going to die very quickly, because the time constant of that is going to be very short. So the response of the system will be predominantly because of the second order system. So that's what they are giving you, basically a threshold, that if 1 over zeta is greater or equal to 10 times zeta omega n. So if the difference between the two is 10 times, if we assume zeta omega n, assume omega n is not 1, in this case we are assuming omega n is 1, but if omega n any value, but if the difference between the two is 10 times, so if it is 2, and if this thing is 20 or more than 20, then this factor is not really going to affect the shape of the second order system, because the exponential function associated with the third root, because this is going to be an exponential function and this is going to be an oscillatory exponential function. So the exponential function associated with the third root, it is going to die down very quickly. It's not going to really affect the shape of the second order system. But as you start moving this root closer and closer to this, then definitely it is going to affect the shape of the second order system, because the difference between the two may not be that much. So when you add the response of exponential response associated with that third root and the second order response, when you add them together, then it's going to be quite different than just the response by the second order system. So that's what it is discussed here as when it's okay to kind of ignore the third pole and assume that the response will be solely because of the second order system. And the criteria that is given in the book is this criteria. If 1 over delta is greater or equal to 10 times zeta omega n, then most of our parameters can be, most of our performance indicator can be safely calculated using only the second order system, ignoring the third order pole, basically. So percent overshoot, settling time, and all those things. If this criteria is valid, then you can just use the second order system and calculate all those things, assuming that the curve, because of the third pole, died down very quickly. Yes. Then you don't have really second order system, it's just going to die quickly. Yeah. So the whole idea over here is when you're calculating peak overshoot and stuff, that is associated with the second order system. So we are trying to see that if you do have the third pole, but if you want to use those equations that we discussed, or you want to use the second order curve and then observe all those values, when the third order starts affecting that curve, basically. So when it's going to affect the peak overshoot and all those things. So what the criteria that we are setting is if that third order pole is far enough, given by that, then basically we can safely calculate everything only because of the second order system, ignoring the third order pole. But as it starts moving closer and closer towards the second order pole, as you can see over there on the x-axis, as 1 over zeta, 1 over gamma start getting closer and closer, then it's going to start affecting the second order curve, basically. And then you can no longer use the equations. You can still use the plot, because plot, of course, you can always observe values. But the equations that we use were purely from the second order plot. So you will no longer be able to use those equations to calculate the peak overshoot and the peak time and stuff. Yes, you can plot it, and then from plot you can observe it. But equation calculation and the plot are going to give you different values. Mm-hmm. Yes. As your second order. So you don't really have to rewrite it. You can just, because the whole thing is to observe, to calculate the performance parameters, what the peak overshoot and stuff. So even if you don't want to rewrite it, if you use those equations that we discussed in the last slide, you can just use those equations and then calculate the peak overshoot and stuff. And those are going to be very close to the actual values if you plot the system, including the third order pole. If you plot the whole system, the values are going to be very close. But as I said, if the third order pole starts coming closer and closer, then it's going to affect all the values, and then the calculated values and observed values will be quite different from each other. Okay, transient response is important, and understanding that without going into the calculation, understanding that where your poles are located, poles basically determine how the transient response is going to be. So where your poles are located on the S plane, if you have that understanding, so this is the S plane, and of course you have real values, you have negative real values, and you have imaginary values and negative imaginary values. So remember, S is sigma plus j omega. Sigma is on the real axis and j omega is on the imaginary axis. So depending upon where your poles are located, remember again, poles are the roots of your denominator of the transfer function. So where the roots of the transfer function, the denominator of the transfer functions are located, you can tell how the response is going to look like without going into the actual values of the response. But you can tell about the shape of the response, the transient response, if you know where your poles are located on the S plane. And that's important to understand. That is, if the response is going to be overdamped response, underdamped response, how fast oscillations are going to be, how fast it is going to go down through the exponential function. If it is an unstable response, if its output is going up instead of coming down. So all those things, if you understand about if your poles are located in one of those 4 quadrants and how far or how close they are located, then you can understand how the shape of the response is going to look like without doing the mathematical calculations. Of course, mathematical calculations are going to give you the actual values, but as long as you have understanding about the shape, then you can design the system safely without actually going into the mathematical value. Anytime you have complex conjugate poles, then remember that you have 2 poles that come together. one is going to be on top, one is going to be at the bottom, with plus j omega and minus j omega. Again, dominant pole is going to be the one which is closer to the origin on the real axis. That's going to be the dominant pole, and dominant pole is going to define the exponential decay of the curve, or exponential response of the curve. So let's move to this figure and then discuss from this figure action. Or maybe I can, I can insert a slide and then explain it. Let's go ahead and insert a slide here. Insert a slide. And then on this slide, I'm going to draw one by one and then discuss that. So the first thing is, this is your S-plane. If you have, again, if you have only real poles, so you have these poles basically, you have real poles. Real poles are going to produce what type of response? Exponential transient response, e to the power negative alpha, right? So if you have let's say -1 and -3, then your exponential response corresponding to this is going to be simply e to the power -t plus e to the power -3t. Which one is going to die faster? E to the power -3t, because the time constant associated with that is going to be 1/3, and the time constant associated with e to the power -3 is going to be 1 second. So 1/3 is a smaller time, it's gonna go down faster than the one that is e to the power -t. So anytime your poles are real on the negative x-axis, your transient response is going to go down, and eventually it's going to go down to 0, right? Anytime you have poles real, but those poles, or at least one of the pole, is on the positive axis, you need only one pole on the positive axis. So let's say you have e to the power 2t. Then what's going to happen? I mean, not e to the power 2t, sorry. You have s is equal to 2. So remember, this is s is equal to -3, -1, 2. Then your response corresponding to this will be e to the power 2t. And anytime you have this response, it means that your curve is going up, your transient response is going up. So your system is going to become unstable. As time passes by, it's going to start increasing, start going up, and the system is going to be unstable. So it is important to realize that anytime you have the real values on the negative side of the S-plane, remember this is the S-plane, anytime you have the real values on the negative side of the S-plane, what we call the left side of the S-plane, your system is going to be a stable system. The transient response is going to go down. And anytime you have values for the roots, the real values of the roots on the right side, then your system is going to become unstable. That is, your transient response is going to go up instead of going down. So having this understanding is, again, important, that if you look at your real root sigma value, remember sigma plus j omega. So if you look at just sigma, and if you only have sigma, if you don't have any j omega, that's fine. But if sigma is negative, then transient response is going to go down, exponential transient response is going to go down, and positive exponential transient response is going to go up. If you have roots, on the imaginary axis, so, and remember the roots come in the complex conjugate whenever they are going to be complex. So once again, this is j omega and this is sigma and j omega. So in this case, imaginary poles. Anytime you have imaginary poles, let's say negative J2 and positive J2. Let's assume that let's say there is no sigma, just imaginary poles. Your transient response is going to be a sinusoidal response, sustained sinusoid. It's going to be a sustained sinusoid with the frequency of 2 radian per second. So your transient response is going to have the shape sine of 2t or cosine of 2t. Omega n value is going to be 2, and it's going to be a sustained sinusoid. And it is stable because sustained sinusoid is assumed to be a stable response because it's not blowing up. So that's what happens when you have imaginary poles for a transfer function. Now, if you have now this, let me go back. The system is going to be actually critically stable. Critically stable means that it may be stable or it may be unstable based upon how you respond, how your input is. So if your input, let's say, is a step function, then your system is still going to be stable because your system output is going to have the transient response of sine 2t, and the step response is going to produce a DC value. So basically, it's going to be, the output will be a sinusoidal value which is offset by a DC value. If your input is a step function, and then you have two complex conjugate pole on the y-axis. But if your input is also a sinusoidal function with this frequency, which is the same frequency produced by your poles of the transfer function, then your system is going to become unstable. Because anytime you have multiple poles located on the y-axis at the same point, the system is going to become unstable because the output is going to be in the form of t sine omega t. So that t is going to start increasing, and your sinusoidal function will keep on increasing as time is increasing. So in this case, we call the system to be critically stable system, and we say based upon the input we can decide if the output will be stable or unstable. So system is called, from the transfer function, system is called critically stable system, not stable or unstable, but it is critically stable if your poles are located on the y-axis or j omega axis. So this is a critically stable system. And we're going to do some examples. Yes. Yeah, then that's fine. Your system is going to be stable if they are the same locations. For example, if your input. So right now I'm plotting the poles for the transfer function. Remember, output is transfer function times input, right? So this is only the poles of the transfer function TS. Now output is TS times RS. Now if RS also produce poles at the same point on the y-axis, in that case your output is going to become unstable. But if your RS is a step function pole is going to be where? It is going to be 1 over S. So the step function is going to produce pole at S is equal to 0 right here. It is still on the y-axis, but it is not at the same point as J2 and negative J2. So the output is going to be, output of the system is going to be a stable output. The system is still called critically stable system. But since the third pole, which is coming from RS, is not at the same point as these, the output of the system is going to become stable. Output, as I said, is going to be have one step function and one sinusoidal function. So that when you combine these two, is going to be a sinusoidal output which will be offset by a DC value. So that will be considered as a stable output because it's going, back and forth between the two limits. Unstable output is always which is blowing up as the time is increasing. But if the output is constant, or if it is sinusoid, or it is going down, those are the stable outputs. Now, the problem is when you put your output Rs as a sinusoidal function and take the frequency of that sinusoid to be the same, 2 radian per second. Then you will have 2 poles from Ts at J2 and negative J2 and 2 poles from Rs at J2 and negative J2. So now you have repeated poles on the y-axis at the same point. And that will result in the time domain a function which will be T sine of T2, something like that. And that T, when you put time, it will linearly increase. So the output is going to be linearly increasing sinusoidal function. And that will make the output to be unstable. Right? And again, as I said, we will do some examples so that you will actually see the time domain output. But at this time, I'm saying just understand the location of the poles and their effect on the output to make the system, how it's going to look like, stable and unstable, how the output is going to look like, and all those things. So for these, of course, you have the exponentially decreasing output, exponentially increasing output, sinusoidal output, sinusoidal transient response, not output, sinusoidal transient response. All right, third is if your poles of the transfer function are complex conjugate. Of course, if you just have one pole at s is equal to 0, that's going to produce a step function, but it's also a critically stable system. So this is going to, if you have a pole at s is equal to 0, then it is going to produce a step output, not going up, not going down, not sinusoidal, but a step output for the transfer function. And then if you excite that system with a step input, if Rs become a step as well, then you will have 2 poles at s is equal to 0, one coming from Ts, one coming from Rs. And again, your output is going to become unstable because you will have 1 over s square. And if you look at in the table, 1 over s square, actually you don't have to look in the table. If you look here at the beginning of this chapter, right here, 1 over s square is going to produce an output A times T. So if 1s is coming from your transfer function and 1s is coming from your Rs, then your output is going to be unstable. It's a linearly increasing output. But if you have 1s, that is if your transfer function is a step function, so you have the pole at s is equal to 0, but if you're exciting that system, if your input is a sinusoidal function, then your output will still be a stable output because now your poles are not going to be aligned. The Ts pole is going to be at s is equal to 0, and because of sinusoid, your input poles are going to be, let's say, at J2 and negative J2 or something. So all 3 poles are going to be at different spots on the y-axis. So again, your output is going to be not linearly increasing, but it's going to be a sinusoidal output offset by a specific DC value. So this is dangerous. Critically stable system, they are dangerous in the sense that you have to be careful as what input function you're going to use to excite those systems. If you don't use the proper input function, then your system can become, your output can become unstable. But as far as Ts is concerned, if your Ts pole is on s is equal to 0 at the origin, then it's going to correspond to a step function, constant value. And now finally, if your Ts value, they are complex conjugates. So they are here or they are here on the left side of the S-plane. So now you have both the value of sigma and the value of j omega. So we have j omega 1 and j omega negative j omega 1. So you have sigma plus j omega 1 as this pole, sigma plus j omega 1, and sigma minus j omega 1 as this pole. And again, as we know, this is going to result, this is a second order system. So this is going to result in exponentially decreasing sinusoidal function. As sigma value as close this value to, so this is, let's say, sigma 1 and this is sigma 2. As we discussed, as close this value to the origin, the response is going to last longer, and as this value is going to move away from the origin, the response is going to die quicker. As far as the effect of omega is concerned, higher the value of omega, more oscillations are going to be there before it dies down, because higher the value means your frequency is higher. So you have more oscillations within one time period. And lower the value of omega is going to be less oscillations in the response. So in this case, you have to look at both sigma value and omega value if you have multiple values, and decide which one is going to die faster, which will have more oscillations, and so on and so forth. The system is going to be stable because all the roots, all the real values of sigma are on the left-hand side of the plane. So the system is going to be stable for any value of the input, any stable value of the input. And the nature of the response, of course, is going to be the oscillatory response that is going down, exponentially decreasing response. How many oscillations depend upon the value of omega? As I said, a smaller value, less oscillations, higher value, more oscillations. Yes? Duplicate of the two poles on the real axis? What do you mean? Oh, s plus 1 is square. That is going to produce, so that's going to give you 1 over s plus 1 plus 1 over s plus 1 is square. So it's going to produce a response which is going to, it's going to be, I believe it's going to become unstable. Let me see. I'm trying to think about the table. In the table, we have 1 over t plus 1 is square, and that's going to be t e to the power negative alpha t or something like that. So it's going to become unstable if you have multiple poles at the same point on the real axis. Yeah. It rarely happens though. We don't really have multiple poles on the real axis. It rarely happens because your input is usually not an exponential function, sinusoidal, exponentially decaying function. Your input is usually a step function or sinusoidal function. So generally, it does not happen. All right, and then if you have, of course, yes, Stephanie. Yeah. Transfer function and the input signal, yeah. Generally, again, as I said, generally we go with the transfer function to determine what type of, because the transient response comes from the transfer function. Steady state response comes from the input signal. Because once the transients are gone, you are only left with what type of input you're supplying to the system. If it's a step input, when the transients are gone, you only are left with the step input. So the steady state value of the output comes from the input, and the transient value of the output comes from the transfer function. If we have roots, of course, on the right side, complex conjugate roots, what type of response we are expecting? Anyone can tell me? Sigma plus j omega 2 is going to be exponentially increasing, and it's going to be oscillating in nature. Yes. So it's going to be poles. Yeah, poles of the denominator. I mean, roots of the denominator. So poles. So it's going to be, as you know, said, it's going to be increasingly oscillating exponential function. Instead of decreasing, it's going to be increasing. So the system is going to be an unstable system. For any stable input, it's going to start increasing. Exponential function is increasing. And of course, again, frequency of those oscillations are going to be higher if the omega value is higher. And sigma value, the higher the sigma value, the faster it's going to be increasing. So this is how you are going to kind of envision, based on the poles of the transfer function, how the transient response of the system is going to look like. Again, without going into the values, just the shape of the transient response. And this is, I believe this is from the book. So this is given location of different pole and corresponding frequency of the underdamped responses and speed with which the transient response dies off. So again, you have real poles, as we discussed. You have the decaying exponentially decaying transient response. Farther the pole is going to die down quickly. Closer the pole to the origin is going to take longer. If you have a pole at the origin, step response, as we discussed. If you have a pole on the right side of the S-plane on the origin, increasing response. Complex conjugate poles. So omega value is the same for each one of them. Sigma value is changing. As you can see, the frequency of the sinusoids is going to be the same, except this is going to die down quickly and this is going to last longer. So you will have more oscillations that you can see. If it is dying down slowly, you can see more oscillations, but the frequency of oscillations, it is going to be the same. And if you increase the omega value instead of the value of sigma, if you increase the omega value, then the frequency of oscillations are going to increase. The exponential decay is still going to be the same, corresponding to this, and this will be same, but frequency is going to increase. So this is what basically I discussed with you. They're showing you different. So marginally critically stable and marginally stable is the same thing, and here I'm putting marginally stable, but it's the same thing as critically stable. Pair of complex conjugate on the j omega axis will result in sinusoidal transient response. Therefore, the complete response will be sinusoid with a DC offset if your input is a DC value. So in the next chapter, we're going to discuss the stability. So we're going to discuss marginally stable and all those. But I gave you basically an introduction to that as how the system how the output is going to look like based upon where the roots are located. Steady state error of feedback control systems. We discussed steady state error earlier. Steady state error simply is based upon the system. It is simply 1 minus T naught, 1 minus transfer function evaluated at T is equal to 0. That's your steady state error for a step input, that is, for a step input. So for a step input, the steady state error simply is 1 minus T0. But in this, under this topic, we're going to look at if your input is a step, ramp, parabolic and stuff, then how the steady state error is going to be. And this also deals with numbering of the system. You give a number to a system based upon some parameters, as we're going to discuss. So the error signal for a unity feedback system, we have a unity feedback system right here, is given by 1 over GCS GS RS. Now remember, this equation is coming from ES is equal to RS minus YS, and YS of course is ESRS, and transfer function of this is 1 minus TS, and transfer function we know is GCS GS over 1 plus GCS GS. So once you plug in this transfer function over here, and then 1 minus that, you simplify that, you're going to be left with 1 over 1 plus GCS GS RS. So the the tracking error in the Laplace domain simply can be given by that expression, 1 over 1 plus GCS GS times RS. And if you apply the final value theorem, then you can calculate the steady state response, of course, based upon whatever the value of RS is. Right now, we are not assuming any specific signal, input signal, a step, ramp, parabola. We're just showing that this is how you can calculate the steady state value, S tend to 0, S times steady state error, which is 1 over 1 plus GCS GS RS. Now we're going to take different values of RS, and we're going to see how the steady state error is going to be. So first, we're going to take a step input. So R is equal to A times UT, RS is A over S. So we use the same equation right here, and we plug in the value of RS over here, expression for RS over here. So steady state limit S tends to 0, S times AS, S times A over S, 1 plus GCS GS, and S and S are cancelled out, of course, A over 1 over. And since GCS and GS are the only function of S, so we can move this limit to GCS GS. So A over 1 plus limit S tends to 0, GCS GS. And GCS GS is the loop transfer function, what we discussed earlier. LS is equal to GCS GS. And the general expression of the loop transfer function can be given by this expression. So you have zeros on top with a gain, and you have poles in the bottom, and you have multiple values of poles at Z is equal to 0. So in general, the loop gain expression in general can be given by K S plus Z1 times S plus Z2 S plus Zm. So you can, the numerator polynomial, you can make factors of those numerator polynomial and write down that K is the gain. And then denominator polynomial, S to the power n, based upon what type of input you're using. S plus P1, S plus P2, all the way up to S plus PK, S plus PK, not PK, sorry, S plus PQ. PQ is the last value. The loop transfer function, once you have it, and you can have any loop transfer function. For example, you can have S cube plus 5S square plus 6S, 2 over S4 plus 9S cube plus 5S square plus 7S plus 8. Let's say you have this loop transfer function. So you can factor out the numerator, you can factor out the denominator, and you can write this down in terms of this. And assume, you have some poles at the origin as well. So this is a generic loop transfer function. You can have no poles at the origin, you can have one pole at the origin, whatever you want. In 5.16, the transfer function has m distinct 0, q distinct poles. In addition to that, there are n poles at the origin, s to the power n. N represent the type number of the system. So the number of poles that you're going to have at the origin, that will represent the type number of the system. So once again, this is when RS is equal to A over S. Right now, that's that case we are discussing for the unit step input. So if your input, if the number is 0, the type 0, that means you have n is equal to 0. That is no pole at the origin. So your S0, that means that you have no pole at the origin for type 0 system. And your steady state error is given by A over 1 plus GC naught, G naught. A over 1 plus K, multiple of all the zeros divided by multiple of all the poles. So again, if you go back here, GCS, GS, we take S to the power 0, 1. So this whole thing is going to come over here. And since S is equal to 0, when you're evaluating at S is equal to 0, all the S are going to become 0. That means we are multiplying all the zeros together in the numerator and all the poles together in the denominator. And the result is going to be this. So GC0, G0, we are calling it position error constant, Kp. So Kp is when limit S tend to 0, GCS, GS. And a steady state error for unit step input in terms of position error is given by A over 1 plus Kp. This is for type 0 system with step input. Type 0 system with the step input. For any other type system, 1, 2, 3, the steady state error will be what? So again, we have, let's say we have type 1 system. So S to the power 1. So if we go and replace this by K times multiple of all zeros divided by S multiple of all the poles, and we apply the limit S tends to 0, what will be our result? So for type 0 system, as we discussed, for type 0 system, the steady state error is A over 1 plus Kp, where Kp of course is the position error, which is K times multiple of all the zeros divided by multiple of all the poles. If we still keep the same input, if we still keep the step input, but if we choose the system to be type 1 system instead of type 0 system, what will be the steady state error? That's right over here. For any other type of system, 1, 2, 3, the steady state error will be. Now, how are you going to figure that out? Again, if you look at the steady state error for type 1 system, it is going to be E steady state A over 1 plus K product of S plus Z's, not a steady state, ES. ES divided by S product of S plus poles. So this S over here, S to the power 1, this S represent type 1 system. So if you have type 1 system or type 2 system or type 3 system, what do you expect that your output is going to be? What do you think? Put S is equal to 0. Remember, a steady state out for a steady state error, what you're doing? You're putting S is equal to 0, right? I forgot to put limit S is equal to 0, basically right here. Limit S is equal to 0. GCS, GS. Limit S is equal to 0 is going to come here. 1 plus limit S is equal to 0. This is steady state. When you put limit S is equal to 0, what you're going to get? 0. You're going to get 0 steady state error. What if your system is type 2, S is square? Still zero. Still zero. So anytime your input is step and your system is type 1, 2, 3, 4, whatever, your steady state error is always going to be zero. It is going to be non-zero only if your input for step input, if your system is type 0 system, then you have non-zero steady state error. But if you have any other type, then your steady state error will always be zero. Because your denominator here, remember this S is representing the type of the system. S1, S to the power 1, type 1 system, S to the power 2, type 2 system, and so on and so forth. So that factor is going to become infinity. 1 plus infinity is infinity, and A over infinity is going to be 0. Anytime you have S is equal to 0 for type 1, type 2, type 3, type 4, whatever. So your steady state error will always be 0 for a step input. What about for a ramp input? So ramp input is given by A times T ut. Rs is equal to A over S square. So steady state error, limit S tends to 0, S times A over S square 1 plus GCS GS. 1 S power is going to be cancelled by 1. And you're going to be left with A over S plus S GCS GS. And if you put S is equal to 0, so this S is going to become 0, and you're going to only be left with A over S GCS GS for the ramp input. This is your steady state error expression. Now, based upon the type of the system, you will determine for ramp input how the steady state error is going to be. Either it's going to be constant, it's going to be 0, it's going to be infinity, whatever. So for type 1 system, again, the steady state error can be given by A over S, which is there, and type 1 system is represented by K times the product of all for type 0 first, for the type 0 system, when your S is equal to when you don't have any poles at S is equal to 0. For type 0 system, what is going to be the steady state error? Who is going to tell me? So remember, for type 0 system, this is 1 right here. Right? This is 1 for type 0, S to the power 0, which is 1. So what will be the steady state error from this equation? What do you think the steady state error is going to be when you put S is equal to 0? Infinity. Infinity. So the infinity means what? The difference between the steady state value of the input and output will just keep on increasing as the time is progressing. So for type 0 system with your ramp input, the steady state error is going to be infinity. If you have a type 1 system, S to the power 1, this S to the power 1 is going to be cancelled out by this S, and you will be left with A over product of all the zeros divided by product of all the poles. So for type 1 system, steady state error with the ramp input is simply given by this expression. And we call Ky as, or Kv, sorry, as velocity constant, velocity error constant, which is simply given by limit S tends to 0, S times GCS GS. For type 1 system. For type 2, 3, 4, what do you think the error is going to be? For type 2 system, 3 system, 4 system, so you are increasing the value, the power of S over here. What do you think the error is going to be? For, no, what do you mean step 1? It's going to be 0, not type 1, because when you're putting s square, let's say, right? So 1 power of s will be cancelled out by this 1 power. So it's going to be denominator is going to be s. So that's going to become 0. So the whole denominator is going to become infinity, and a over infinity is going to be 0, right? So for type 2, 3, 4, all the upper type systems, for your ramp input, your output, the steady state error is going to be 0. And the final and last input is if we have a parabolic input, acceleration input or parabolic input. So your input is a times t square over 2n, and your Laplace transform of that is going to be a over s square. It's not n. A t square over 2. Laplace transform is going to be a over s square. And once again, we calculate the steady state error for type 0, type 1, type 2 system. So steady state error, as you can see, s times a over, it's going to be s cube. Power 1 power is increased. S cube. This is incorrect. S time a over s cube, 1 plus GCS GS. So it's going to be a over s square plus s square GCS GS. And when you apply limit s tends to 0, then it's going to be reduced to a over s square GCS GS. Again, I did not show one step. The middle step is going to be limit s tends to 0, a over s square plus s square GCS GS, once you simplify that. And when you put s is equal to 0, this is going to become 0, and you are left with a over s square GCS GS. So for type 0 and type 1 system, what we are expecting. Again, type 0 system and type 1 system. We'll go back. Perhaps I can write this down here. So what steady state error is limit s tends to 0, a over s square, product of all the zeros divided by, for types, so s to the power n, product of all the poles, product of all the poles, right? So now apply type 1, type 2, type 3, whatever you want to apply. For type 0 system, s to the power 0, what will be the steady state error? It's going to be infinity, because you have a over s square, which will be 0, times a constant value. So that's going to be infinity, because you have 0 in the denominator. For type 1 system, s to the power 1 instead of s to the power 0, s to the power 1. So it's still going to be infinity. Now for type 2 system, s square and s square will cancel out. And your error is going to be a over product of all the zeros divided by product of all the poles, as you can see over here. So this is going to be infinity for type 1 and type 0 system for a parabolic input. And for type 2 system for parabolic input, you have a constant value, a over k time product of all zeros divided by product of all poles. We are calling this Ka, which is our acceleration error constant. Limit s tends to 0, s square GCS GS. And type 3 and higher system, of course, is going to be, anyone? 0. So type of the system depends upon how many poles do you have at origin from the transfer function, from the loop, sorry, not transfer function, from the loop gain, for the loop gain. And then for different inputs, step, ramp, and parabolic. you have different steady state error for different type number of the system. So this table shows you, of course, what we discussed. For type 0 system with a step input, you have a constant error. For ramp input, parabolic input, you have infinite error. And then for type 1 system with the parabolic input, for the step input, you have 0 error. For parabolic input and ramp input, you have, for ramp input, you have constant, and for parabolic, you have infinity, and so on and so forth. For the non-unity feedback system shown in figure 5.9, calculate the steady state tracking error given GCS is equal to 40, GS is equal to 1 over S plus 5. K1 is equal to 2, HS is equal to 20 over S. Assume the input to be the step input. So it's a simple problem. The first thing we're going to do is to write down the transfer function. All right, what will be the transfer function of this thing? It's going to tell me. K1 is the gain, which is multiplying your input and coming here, adding with everything. Very good. So K1 is, of course, the gain, input gain. So that's going to be K1 times the transfer function of the feedback system, which will be GCG over 1 plus HGCG. And that is multiplied by your input gain K1. Error is RS minus YS is equal to 1 minus TS RS. And a steady state error for a step input, since it's a step input, can be given by 1 minus E naught one minus K times GC naught G naught over 1 plus H naught GC naught G naught. Again, S is the frequency, remember. So right now we are evaluating everything at DC. S is equal to 0 is DC. If the function is changing with respect to frequency, you're gonna, of course, put S is equal to 0 and then find the value. If the function is not changing with respect to frequency, then it's gonna be the same value, constant value. So 1 minus K times, and K is K1, sorry, K, it's a K1, not K. It's K1. K1 is given as 2. So 1 minus 2 times GC naught is 40. So that's a constant value. GS is 1 over S plus 5. So when you put S is equal to 0, that's going to be 1 over 5 divided by 1 plus H is 20 over S plus 10. So 20 over 10 is 2. S is equal to 0 times GC naught. Again, GC naught is 40. And G naught is 1 over 5. So your steady state error is going to be 1 minus 5 8s are 40, 8 times 2 16 divided by 5 8s are 40, 8 times 2 16 plus 1 17. 1 minus 16 over 17, whatever the decimal number is going to be. That is going to be your steady state error. So steady state error 16 over 17 is close to 1. It's not exactly 1. So steady state error, remember, is supposed to be 0 in general. We want at the steady state the output and input to look exactly same. In this case, they're not. They're close to 1 because 16 over 17 is what? 0.9, 0.8, something like that. I don't know. 0.94. Okay, so that's going to be 0.06 then, 1 minus 0.94. So 6% steady state error you have, which is again very small. Usually with the practical system, you don't expect to be exactly 0 steady state error because of all the disturbance and noise that is going on. But 4% or 6% steady state error is very good. It's acceptable. Let's see. Let's delete this. Okay, determine the value of the controller gain K to yield 0 steady state error in the control system shown in figure 5.10. Assume input to be unit step value. Let's look at that. So once again, our system is non-unity feedback system, and the error, of course, is going to be 1 minus Ts times Rs, and the steady state error input is still unit step. Steady state error is going to be 1 minus T naught. So now let's look at T and then put the values. So 1 minus T naught is going to be what? K times 1/2, so K over 2 in the numerator, divided by 1 plus K over 2 times 2 over 4, right? 1 plus K times, so controller GC, so GC, G, and H. GC, G, and H. So K times 1 over 2 times 2 over 4. So 2 over 4 is 1 over 2 as well. So K over 4, right? K over 4. And we want the steady state error to be 0. So we're going to equate this by 0. 0 steady state error implies 0 is equal to 1 minus K over 2 over 1 plus K over 4. That is going to be K over 2 over 1 plus K over 4 equals 1. We can simplify this, it might be easier. That's going to be 4 plus K and then 2. So 2K over 4 plus K. So 2K over 4 plus K equals 1. So 2K is equal to 4 plus K, and am I doing it correctly? I'm missing something. Four plus K. I think I'm doing it correctly, right? Am I missing something? I'm sorry? 4 plus K over 4. So this 2 and 4 will cancel out. This 2 is going to go in the numerator. It's going to become 2K. I'm assuming I'm doing it correctly, right? So that's going to give us 3. K is equal to, so K is equal to 4 simply. K is equal to 4. 2K minus K is equal to 4. So K is equal to 4. So the controller gain of 4 is going to yield a 0 steady state error. If it is not 4, then you will have some steady state error. Any question about this, guys? All right, some of the performance indices that we have. Performance index is a quantitative measure of the performance of a system, and it's chosen so that emphasis is given to the important system specifications. System is an optimum system when the system parameters are adjusted such that index reaches an extreme value, which is usually the minimum value. So one of the performance parameter is integral of the square of the errors, ISE, which is from 0 to t. T is usually the settling time. From 0 to settling time, square of the error in time domain over dt. We have figure 5.11, and it shows the different performance indices that we're going to discuss. We discussed ISE. Then you also have IAE, integral of the absolute magnitude of error from over settling time, integral of the absolute value of error, integral of the absolute error, ITAE. Index is able to reduce the contribution of any large initial errors as well as to emphasizing errors occurring later in the response. To emphasize errors occurring later in the response. The index provides the best selectivity of the performance indices. Over one settling time, integral of t times the absolute value of the error in time, dt. And then finally, we have integral of time squared error, TE squared. So these represent a graphical representation of all the errors. This is your input, which is your step function A, your output, which is an oscillatory function, and we want the output to have the steady state value of A. Your error function, which is the difference between this and this. And then this is E square T, right here. And this is the integral of E square T. So this is your the error that is here, integral of the square of the error. Many times it is not easy to calculate the integral, of course, unless you use MATLAB or calculators and stuff. So in MATLAB, there is a function, and I forgot, but there's an integral function. Anybody remember that? Whoever took the power electronics must have used it, integral function. We use, but if you took it with me, we used integral function. I think it's integral, but you have to set the integral with a specific way, and I forgot how to do that. I can always figure out, because not always this is easy to do manually. You have to use you have to use program and numerical integration functions basically. But these are some of the indices that we use in order to measure the performance of control systems. All right, let's see. This is a very long example, if I remember correctly. Let's see. Yep, it's a pretty long example. Let's do this. Okay, let's just start this, and hopefully we'll be able to finish it. And you know what time it is? 12:01. Yeah, let's try to finish it. Let's try to add some slides. Okay, what is this example? Hubble Space Telescope control. Consider the model of the telescope pointing system shown in figure 5.1. Goal of the design is to choose K and K1 such that these three conditions are met. The percent overshoot of the output to a step command, the output should be output, not out. To a step command is less than 10%. A steady state error to a ramp command is minimized, and the effect of the step function, a step disturbance, is reduced. So we have to basically, in this case, design this and choose the value of the controller gain K, and we have the feedback in the smaller loop. k1. We have to choose the value of those two such that it will satisfy A, B, C three conditions. So let's do that. This is a design problem basically. All right, the first thing we're going to do is when we assume the disturbance to be 0, disturbance is going to be used for the last one. So assume the disturbance to be 0 for the first one. And let's calculate first the transfer function of the first one. All right, who's going to tell me what will be the transfer function of the first one if disturbance is 0? So you have first solve the smaller loop and then the bigger loop. So the smaller loop is going to give you what? Let's say this is GA amplifier, this is GT telescope, and this is, let's call this H. So the smaller one is going to give you GT over 1 plus H GT. Let's call this G. So this is going to be G times GA over 1 plus G times GA. Which will be GT over 1 plus H GT times GA over 1 plus GA GT over 1 plus H times. Simplify it so that it can be cancelled out. So transfer function in simplified form we can write as 1 plus HGT, and then this is gonna go here, 1 plus HGT, so that's gonna be cancelled out. You're gonna be left with GA times GT over GA times GT plus H GT plus 1. Let me see if I make any mistake, let me know, mathematical mistake. If I simplify this, I think that's what we're gonna get, right? GA times GT, and denominator is 1 plus GT, so 1 plus GT, and that's cancelled out. Seems good. And then, oh, I did not put down the specific functions of G and GT. Let me see what they are. So, what are those functions? Interesting. Okay, let me see. Let me figure out what those. Oh no, this is given here. 1 over S square. Okay. So amplifier is K, GA is K. Let's do it here. Is equal to K times 1 over S square. So K over S square divided by GA GT. So K over S square plus H GT, which is K1S times 1 over S square. So K1S times 1 over S square is going to be K1 over S plus 1. So when you simplify this, we're going to be left with K over S square is the common factor, which will be cancelled out by this S square. So that's going to be K plus K1S plus S square, or S square plus K1S plus K. That's my transfer function. If you have any question, let me know. Looks good. Now we have to excite the system with a step command for the first one, and we have to calculate the value of k and k1 such that your peak overshoot is less than 10%. Okay, let's see. I'll go back. Or actually, we don't really need to do the input. We can just look at the transfer function and figure out. Our transfer function is k over, let me write down. Transfer function is k over s square plus k1s plus. All right, so if we compare this with our standard second order system, omega n square, s square plus 2 zeta omega n plus omega n square s. If we compare these two, then we can see that, of course, k is equal to omega n square, and then we can find out what k1 value is. So in this case, k is equal to omega n square, omega n is equal to k, square root of k, and k1 is equal to 2 zeta omega n, and omega n is the square root of k, so zeta value is k1 over 2 square root of k. So we're going to figure out what are the values of k1 and k such that our peak overshoot is, so let's go back. Peak overshoot is 100 e to the power negative zeta pi over 1 minus zeta squared. That's the equation that we discussed earlier for the second order system, the peak overshoot equation, if your input is a step function. If we keep this peak overshoot to be 10% maximum, let's say maximum value 10%, right? And again, this is the percentage. Both of them side are in percentage. So we're going to get 0.1 is equal to e to the power negative zeta pi over square root of 1 minus zeta square. Let's do it here. And we take natural log of both sides. Natural log of 0.1 negative zeta pi over square root of 1 minus zeta square. And there is going to be natural log of 0.1 divided by pi is, and of course, the natural log of 0.1 is going to be a negative value. So negative is going to be cancelled out. This is coming out to be 0.7329. 0.7329. It's going to be negative 0.7329, but negative and negative is going to cancel out. that we discussed as how far that third pole is. Remember, we discussed effect of the third pole. If that pole is far enough, then you can still estimate the transfer function using a second order system. But if that pole is close, then really you will have to go and plot the system. You cannot just use this expression as the peak overshoot value expression, basically. Then you are going to calculate, well, you're going to calculate the transfer function and the response, and then plot the step response. I mean, you can still plot the step response without calculating the time domain expression using the step function in MATLAB, but you cannot use the equations. These equations are specifically for the second order system only. So if your third pole again is far away such that you can estimate the system as a second order system, then you can still use this expression. But if this is a second order system, this is a second order, there's no third pole. K over S square plus K1S plus K, that's our transfer function, right? So that's a second order system. We want the peak overshoot to be maximum 10% or less. And that's what we are looking for as what value of zeta is going to produce that. And based on that, we know zeta is equal to K1 over 2 over square root of K. So from that, we can kind of figure out what will be the value of K1 and K. So from this, we can create a quadratic equation, which will be zeta is equal to 0.7329 minus 0.7329 zeta square. And oh, this is a square root. I didn't see that. So we're going to square first on each side. Square each side, we're going to get zeta square. And I'm going to divide this over here. This might be easier, or maybe no. Zeta square is equal to 0.7329, 1 minus zeta square. So we have just, and from this, let me see, zeta square is going to come out to be 0.3495. And zeta, only the positive value, is going to come out to be 0.5912. So any value of zeta greater than 0.5912 is going to result in the peak overshoot to be less than 10%. For zeta greater than 0.5912, peak overshoot will be less than 10%. Remember, higher the value of zeta, less overshoot you're going to get. Smaller the value of zeta, more overshoot you're going to get. So it has to be greater than almost 0.6 in order for the peak overshoot to be less than 10%. Now from this, we can calculate the value of K. Insert a slide. So since we know from our previous zeta is equal to K1 over 2 square root of K. And for peak overshoot to be 10%, zeta is equal to 0.59. So K1 over 2 square root of K is equal to 0.59. This is for the worst case condition, remember. So K1 will be equal to 2 times 0.59. So 2 times 0.6, which will be 1.2. So let me just do 1.2. 1.2 square root of K. for maximum 10% overshoot. Peak overshoot. Now this has to be combined with the second and third condition, the B and C, because again, we don't know right now what is the value. We just established a condition right now, but this has to be combined with the other two in order to have the specific values of K and K1 in order to know what is going to, let's see, what is going to do all these three things, the value of K and K1, 10% overshoot, we established a condition, the steady state error to be a ramp command is minimized, and effect of the step disturbance is reduced. So we'll have to, right now we established only one condition such that this is the condition to do this, but we have to incorporate the other two conditions, and then we're going to establish the value of K and K1 that will satisfy all three conditions. Now, as I said, it's a long problem, so I don't think I'll be able to finish this in the next, 10 minutes that are left. So this is what I'm planning to do. I can, either we can continue this problem next week. By the way, the exam is in 2 weeks, and the exam is going to be from chapter 2, 4, and 5. Next week, we are supposed to start chapter number 6, but that's not going to be part of the exam. Okay. So we can continue the problem next week, or I can solve it and then make it part of the notes and then post it. So you guys can study, and if you have any question, then you can ask me in the next class. We can do that as well. Might be better because you will have time to go over it and then understand it. And if you have any question, then you can always ask me those questions. So I guess I'm going to do that. I'm going to complete this problem, make it part of the notes, and then post those notes. And again, if you have any question about those, then we can discuss it in the next class. Okay. Well, let's do that.